ChemStars, this is Mrs. Vanderlein bringing you the last section about reaction energies, all right? So let's go back. We learned about the Hindenburg last time, all right, and watched it blow up on the YouTube clip, okay? So the question is, where does all that energy come from to blow up the Hindenburg? If you recalled, it was the hydrogen gas in the blimp reacting with the oxygen in the atmosphere, causing that horrendous fire, all right, and all that heat being released, all right? Where did that come from? All right, well, so glad you asked. It's all about the bonds, all right? So we actually are going back to chapter 6. Look at this. This isn't 16.2. This is 6.2. Covalent bonding and molecular compounds. That is not a typo, is it? No. So we're going to go back to chapter 6. And in case you remember, this is that Lewis dot diagram chapter where we drew Lewis dot diagrams. Okay. Oh my goodness. It's been a while, hasn't it? Okay. So let's go to section 6.2 where we talked about bond lengths and bond energy vary from molecule to molecule. So the question is, well, what is a bond? In the covalent bond, it is the sharing between two atoms. The sharing of what? The sharing of electrons. All right. There is an attraction between these two electrons. And I had to do that spin, if you recall. So if there is an attraction, look closely at the wording. You might want to underline this or highlight this. What is that? It requires energy to break the bond. Sound familiar? That means it's exothermic to break the bond. Okay, so let's check this out. Here is the Hindenburg again. Okay, there's your hydrogen gas and your oxygen gas. So let's check this out. What do you need to do first is draw the Lewis diagrams. Oh my goodness. So go find a periodic table, find hydrogen. How many valence electrons does hydrogen have? 1. So if I have an H2, all right, what does that look like as far as a Lewis structure goes? There they are. Why did I write 2 of these? Because I have 2 of them in the equation. So here is my bond, okay? Well, what about O2? It has 6 valence electrons. Go ahead and try to find the correct Lewis diagram for oxygen. Remember, each element besides hydrogen wants 8 electrons around it. Why? That's the octet rule. That's your stability, okay? And so take a few minutes out and determine what the correct Lewis structure for O2 is. You only got 12 electrons to play with. Go for it. All right, this is what I came up with. It's a double bond. All right, and then there are 2 lone pairs on each. Just check 2, 4, 6, 8, 10, 12. I have the right number. All right, and now what? Now you have water. Go ahead and make water. Oxygen has 6, hydrogen has 1. Put it together and see what you get. And this is what I got. Notice I have 2 waters. Why 2? Because that's the coefficient. And there's 2, 4, 6, 8 on each water, okay? So what's happening now? How do you make a reaction? You need to break bonds, and then you need to make new ones. All right, so I need to break up all these bonds here, okay? I need to free them. So bonds must be broken. Now think about it. Imagine if you had, let's say, a pencil. All right, put a pencil in both hands, okay, and snap it. Break that pencil. Does it require energy or does it release energy when you initially break that pencil? It doesn't do it on its own, does it? It requires energy. And what does that sound like? Oops. What requires energy? What absorbs energy? That's called what? Endothermic. And delta H is going to be positive. All right, so if bonds must be broken on the reactant side, what's going to happen on the product side. All right, bonds must be, or wrong one, bonds must be formed. Okay, so if I'm going to put together these elements, all right, so imagine these magnets coming together because there's electric spin going on. These are electrons. So imagine if I have these two magnets coming closer and closer and closer, all right, all by themselves. I don't have to push them, all right. What happens? Ready? They snap together. Did you hear that? These magnets do what? They snap together. And what does that mean? It releases energy. Did you hear that? When I clapped my hands, energy is released. So what does that mean? It is exothermic and delta H is negative. So there's two parts to every chemical equation. You have to break bonds and you have to form bonds. So now the question is, so how do you know how much energy this is going to take? All right, where are these numbers going to come from? How do I know what I get, how much energy is? Well, what do you have to do? You have to look it up. Let's go to the next page. So I can determine whether a given reaction is endothermic or exothermic given a what? A table of bond energies. Well, here they are. You're going to look these up. So that's why you had to draw your Lewis structures so you can determine, do I have single bonds, double bonds, triple bonds? All right, and then you look it up, okay? So these bond energies, here I have this again. So I have bonds broken. Let's check out how many HH bonds do I have? I have one HH bond, two HH bonds. Well, I only got one of these guys, right? How many HO bonds are being formed? 1, 2, 3, 4. I break this apart. Here, I'll do that. I break this apart. I break this apart. I got two of those. I break the HH bond. I break the O double bond, O. And then I'm going to form, this is a new bond, this is a new bond, this is a new bond, and this is a new bond. So I'm breaking two HH bonds and one O double bond O, and I'm forming 4 HO bonds, okay? Well, let's look this up, all right? Find HH up here. Here it is, first one, 432. Okay. Find O double bond O. Here it is, 495. Find OH, 467. So that's where those numbers come from. So here I go. So I have two HH bonds. I have one O double bond O. So it requires 1,359 joules of energy to break all the bonds. I have 4 HO bonds. So 4 times 467 is 1868. So I release 1,868 joules when I form those bonds. So this first one is endothermic, so I make it positive. But when I release energy, it's exothermic. I get a negative. So let's kind of put this together. Do you remember when I showed you this? Oops. That's not exactly how I wanted to end that. Let's erase this. It's supposed to level off. All right, don't know how that happened. There we go, something like that. So, what does this represent? That's how much energy is required to gain, to absorb, to break the bonds. So that's what this number is right here. That's 1357 to go from here to the top of the hump. It requires from the surroundings 1,359 joules to break all those bonds. But then what? Well, let's use, I don't know, green. I don't care. Let's look like Christmas. All right. But wait. That's for that negative 1,868. So when I go from the top of the hump down here, I release 1,868. So do you remember how we figure out what delta H is? All right, well, how about purple, I guess? All right, so what's this value here? That's the delta H, isn't it? That's your difference between this number and that number. Okay, this is your delta H. Okay, that's your delta H. So let's see what happens. So let's get out your calculator, okay? So what is 1,000, let me get my calculator out. Here we go. 1,359 minus 1868. That's negative 509. All right, so this is negative 509. What does that mean? Whoop, that's an O, and that's a 9 joules. That's a 509, believe it or not. It's harder than it looks to write this, okay? So it's negative 509 joules, okay? All right, let's go to the next page. So look familiar? See, chemistry does make sense. So negative 509 is very close to negative 483.6 joules. Where is the difference? The 486, I believe, is where water is a liquid, and the 509 is assuming the water is a gas. All right, so when you use the chart, you have to be in gases, okay? And when we did it before, we had, we're making liquids, so it's going to change that number a little bit, okay? And so that's why it's not an exact number, is because that 486, the water is a liquid. The 509, the water is a gas, okay? And I didn't want to go through and talk about how, how much energy does it take for the liquid and the gas thing, okay? So there you go. Just, hey, trust me, it's close enough, okay? If you account for the changes in states of matter, you would get that negative 483, okay? So let's just put this together, okay? So, excuse me, delta H is equal to the enthalpy of your bonds broken plus your enthalpy or your bonds formed. But wait a minute, because the bonds formed is exothermic, you end up going to subtract, okay? So let's go here and let's practice, okay? So delta H from each reaction given the bond energies on the prior page, okay? So draw the Lewis structures first. And notice what I did. I put the little G here so that we will get the correct answer, okay? It's going to be a water vapor, not water liquid, okay? And so when we're all done, let's determine if this endo or exo. So what is my first step? Draw your Lewis structures. Can you take a few minutes out and try it? So pause this, and when you are done, come back. Okay, I really hope you tried it. So here is what I have. Here's my CH4. Here's my 2O2. You already had O2 down, right? I don't know if you remember, but carbon dioxide is 2 double bonds. And then here's my 2 waters that are a gas, okay? I don't know if it's endo or exo yet. We got to find out. So I have bonds broken and bonds formed. So what are my broken bonds? All right, let's find out. What are my broken bonds? I got to break this, 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 and this, and this, and this. I have 6 total bonds I need to break. Well, how many bonds are formed? Well, okay. I got 1, 2 of those, and 1, 2, 3, and 4 of those, right? Okay, so let's check this out. I have 4 CH bonds, and when I look on that chart, there are 413. I have 2 O2 bonds. When I look up the chart, that was 495. Notice I already put the positives. Why? Because it requires energy to break bonds. Energy needs to be absorbed by the surroundings or from the surroundings in order to break the bonds. So this is what I get. Now, looking over here, I have 2 bonds, 2 C double bond O's formed and 4 HOs. Now, this is straight off the chart, but this is not. Let me show you some. Let's go back to the chart. Now, when I snipped this, all right, off the internet, because the table in your book was not complete, All right. So I decided to go offline or go online and try to find a more complete chart. All right. And you see this little asterisk here? I must, when I clipped this, did not incorporate the bottom like key. There was like probably something down here, asterisk. If it's CO2, this is the only case. If you have a C double bond O and CO2, it is not 745, okay? So I'll say it again. That asterisk here should have had a little key down here, all right? If it is in CO2, each one is what, the 803, I think? 805, okay? So because I made CO2, it's 805. And if you are asked this on any quiz or whatever, I'll make sure that is on your chart, okay? So when I add all this together, I get negative 34466, okay? So what does this mean? All right, I'm gonna start here. And then, actually I should use red, shouldn't I? I'm gonna start here. Okay, and then I'm going to do what? I'm going to add, that's a lot, 2,642. Okay, so that's going up. That's how much energy it takes to break the bonds. All right, now what? I'm going to release energy. Is it more or less than 2,642? I release more. So I'm going to go release more. So I'm going to drop down here. All right. So I end up lower than before. And that's negative 3,466, isn't it? All right. And there you go. So I have a net delta H. Final minus initial is a negative value. So let's check this out. Bonds broken and bonds formed. So my bonds broken is here, positive, because I've absorbed energy to break them. My bonds, did I say right? Bonds broken. This is my bonds formed. I release energy. I have a net 824. So this right here is a net 824. It's negative. It's exo. I release more energy than what was absorbed. And does that make sense? Man, I sure hope so. This is the combustion of methane. All right. So yes, this is how your furnace works. All right. You are burning oxygen with methane fuel. If you guys are getting, your energy from Duke over there and, Duke Energy, you get methane into your house. All right. That's your furnace. That's the gas your furnace uses. So I sure hope it's exothermic because otherwise you're going to get awfully cold in the wintertime. Okay. So yes, it is definitely exothermic. So why don't you guys do me a favor, and there's no exceptions, there's no asterisks, and this is a pretty easy one, okay? Why don't you start from scratch? Do the Lewis dot, do the math, draw your little graph, all right? And so it's going to take you a little bit. When you are done, come back, okay? Do the whole problem. All right, hopefully you finish the whole thing. You learn a whole lot more by trying some of this on your own than just watching me, right? I hope you get that. So if you're just waiting for me to do it, I wouldn't, all right? Do it on your own, okay? So here we go. This is what I got, all right? Notice you have all single bonds, all right? You have single bonds here, all right? So you broke 2 of the chlorine-bromine bonds, all right? So you're going to break these guys up, all right? And you're going to form a single bond chlorine and a single bond bromine. So the math is pretty easy, isn't it? So I have 2 times positive 276, that's to break the bonds, you're absorbing energy. Each bond that's formed is releasing energy, so it's negative. So I end up with positive 552. And when I add these two numbers together, I got negative 432. And when you put them all together, you get a positive 120. So it's endothermic. So let's check this out. Here's my reactants. I'm going to add a total of 522 or 552, right? 550, it's a 5-2, correct? But now what? When the bonds are formed, I only give off 432, right? So notice I'm at a higher spot than I started, right? This is my delta H. Notice my delta H is a positive 120, right? What does that mean? It is endothermic, all right? So endothermic, the net process absorbs energy, okay? The net process absorbs energy. So if you were the surroundings, you're going to get cold. Why? Because the chlorobromine requires energy, possibly from you, all right, which I don't recommend, and you would feel cold. So actually the surroundings will feel cold. Don't be near that stuff, okay? Bad news bears. All right, so that's it. We are done with the thermo unit, even though we go back to chapter 6. Just in case you're wondering why are we jumping around, we're just making sure we cover the standards that the state wants us to cover, and this is a standard, all right? Alrighty, Rose. So don't wait to be great. We'll see you next time. Bye-bye.